Now let's dive into antidifferentiation. What's that? That's a process that undoes differentiation, which is taking a derivative. So undoes means like an inverse operation. So if you remember growing up, we learned how to add. 2 plus 3 is 5. So to undo addition, we would subtract. So 5 minus 3 gives you that 2 back. So it's an inverse operation, similar to multiplication. 2 times x is 10. So 10 divided by 2, to undo multiplication, we would divide, gives you x. And if you want to undo x squared, if you take something quantity squared, you take the square root back. Of course, if you take the square root, it's plus or minus, but that was a different video. So let's look at this inverse operation of taking a derivative called antidifferentiation. And let's start with an example. If I know that the derivative, which is differentiation, of x cubed is 3x squared because of our power rule, then what I can note is if I let little f of x equal 3x squared, what the answer to the derivative is, then an antiderivative of little f of x is going to be capital F of x, which is x cubed. So we do want to pay attention to lower and uppercase f's here. So notation is typical that we use capital F of x to represent an antiderivative. And why did I say an antiderivative, not the antiderivative? Because there's going to be more than one. This is an antiderivative because if we take the derivative back, capital F prime at x is going to be 3x squared, right? And that equals little f of x. However, there are some other functions that would do the same thing. If I had capital G of x as x cubed plus 1, capital G of x would also be an antiderivative of little f of x, 3x squared, because the derivative of x cubed plus 1 is 3x squared as well, because of the derivative of the sum is the sum of the derivatives. Derivative of a constant is 0. I would also notice that if I had x cubed minus 3, that's an antiderivative of 3x squared as well, because if I take the derivative back of this, I also get 3x squared. And of course, I could take any constant, so if I had x cubed plus capital C, where capital C is a constant, and I take the derivative of this thing with respect to x, I notice that I would also get 3x squared, which just makes sense. So if I have 3x squared, looks like this, right? So this is little f of x, but it's also capital F prime at x, where capital F of x is x cubed. So if I had an antiderivative, x cubed is an antiderivative, so here's capital F of x. But if I notice that if I lower my graph or raise my graph, f of x plus a constant plus a positive number would be an upshift. Reducing it, lowering it would be a downshift. If I had any of those shifts going on, then that's fine, because the derivative, which is measures the slope of the tangent line at any point. So if I look here, hey, the slope of the tangent line is positive. It's getting more positive, more positive, more positive. So if I take capital F prime as nothing more than the slope of the tangent line attached to this curve, and what happens is it gets closer and closer to 0 as I get toward the origin, but it gets more and more positive as I get out here. And then as I go left, I notice that it's positive, more positive, more positive, so as x goes left, I get more and more positive here. And whether it's an upshift or a downshift of this, it's going to have the same slope of the tangent line here. So remember, capital F of x, we can just think of as, or capital F prime at x is the slope of the tangent line for our f of x function. So what we then have is a family of antiderivatives. And of course, I always like to think of family being important, right? So always respect your dad and your mom and your parents and your brothers and sisters especially. Anyway, so I capitalize family. That helps remember that. Capital F of x. So the family of antiderivatives is capital F of x plus c. And once again, if I have x cubed plus c, where capital F of x is x cubed, but I add any constant and I take the derivative, I'm going to end up with the same little f of x that I had before. So then we get to a little more formal definition then of what an antiderivative is. So capital F of x is an antiderivative of little f of x on some interval I, if and only if capital F prime at x gives you little f of x back. So the derivative of capital F of x is going to be equal to little f of x for every single x in that interval. And if that's the case, which it was over here for any of these different functions that I had, I actually showed 4 different ones there, then capital F of x would be an antiderivative. So we're also going to have some unique notation with this. So the notation, if you see, I call this a squiggly, but it's a there's a reason for this that we'll get into future videos, but this is called the antiderivative of f of x with respect to x. It kind of looks like a long, narrow s, and that's going to come from a sum, so remember that. So it's kind of a funny looking s, but the antiderivative of little f of x with respect to x is going to equal capital F of x plus c. And so that's going to be true if and only if the derivative of the right side equals little f of x. So anyway, that's a notation. Another word usage of this too, sometimes they use the word integral. So the integral of little f of x with respect to x is capital F of x plus c. So in the future videos, I'm going to give you some theorems, some proven facts, so that we can take antiderivatives very quickly. So just like you know how to take derivatives of functions like x to a power, we're also going to want to be able to undo that and take antiderivatives of those types of things as well.